Integrate with average them and just call it a day.
Okay, from our last class, this is where we start actually. If I go back, see where we were. We talked about the advantages of flame atomizers and the disadvantages of flame atomizers. Usually, the flame atomizers, if you uniform drop the uniform drop sizes, when you do atomization, you have a homogeneous flame and you have required flame and a long path length. The disadvantages, there is a possibility of flashback if you do not control the burning velocity. And remember the burning velocity, if it's greater than the flow rate, then there is a possibility of flashback. That's a disadvantage. And we say that it's a very wasteful process. About 90% of the sample is lost. 90, we say 50, 90, 80, 85 to 95. So about 90% of the sample is lost. And you need a large mixing volume. So those are disadvantages besides the tedious process of preparing standards. Now, the performance characteristics of flame atomizers, we went through this. And I want now to talk about the electrothermal atomization. Electrothermal atomization. So notice here the advantages of electrothermal atomization. And there are several others, but classically, you associate it with the more commonly used method, and that is the graphite furnace atomization. Number one, you notice it provides enhanced sensitivity. And I'm going to put a chart here, and later on, I'll put a chart when I deal with inductively coupled plasma. You see, sometimes it can beat some of these methods in terms of the LOD, limit of detection to which we can go. So the electrothermal atomization provides enhanced sensitivity because the entire sample is atomized in a short period of time, and the average residence time of the atoms in the optical path is a second or more. Usually there are several processes that occur. There is the ashing stage, there's the drying stage, there's a temperature control stage. All those occur very, very fast, all right? So that enhances the sensitivity because the radiation is interacting very quickly with the sample. That enhances your sensitivity. That's one advantage of electrothermal atomization. So if I was to ask you to give me the advantage of graphite furnace, here is one of those advantages that you would pinpoint out. Now, you can see the other one. We have gone through this in the past. I'm just repeating this to emphasize this information again, all right? We went through this. Remember, I said I'm retreading this. Now, the other thing that we talked about is a few microliters of sample are fast evaporated. How much did we say? Give a number. How many microliters, if you remember? About 0.5 microliters, right? About that. So, or up to there, about 0.5, 0.5 microliters. Those are the volumes we are dealing with. What about AA, flame AA? Correct. So it's milliliter level for flame AA versus microliter levels. So you're dealing with smaller volumes in electrothermal atomization. A few microliters of sample are fast evaporated at a very low temperature and then ashed at somewhat higher temperature in an electrically heated graphite tube. So you put the graphite tube within the electrodes. And then once that happens, then the current, notice the two processes there. You evaporate it, and then you ash it. Once you ash it, and then you electrically heat it to another temperature very fast in either in a heated graphite tube or graphite cup, or you have some other platforms Lavivov platforms, which are like cups. Then the current is rapidly increased to several hundred amperes, which causes the temperature to soar to perhaps 2,000 to 3,000. Remember the numbers that we gave, 2,600 to about 3,100. Sometimes it can go to 3,500, okay? So unlike flame AA, what temperature do we use? If you flash back on what we have talked about. If you remember, we gave this table last time.
Doesn't it depend on the reoxidant fuel you use?
Yes, but what is the rough temperature ranges?
3,000-ish.
Can be 3,000, yes, around there. That is, if you're using the flame AA, where you might use acetylene and whichever oxidant that you're using. So notice those are three advantages that we can talk about. It can operate at higher temperatures than the flame atomizers, enhanced sensitivity, lower volumes. And there is another one that is associated with this, which I've not mentioned here, and I would go ahead and mention it. Remember, we talked about the detection limit. The detection limit is much lower than flame AA, and sometimes it's much lower than even the popular mass spectrometry that we use. Okay, so again, here, again, I repeat those kind of samples in this font is smaller, but notice what it's saying. Here you have, you notice here, you have the graphite tube. You introduce the sample from the hole at the top. I showed you the graphite tube, and you introduce the sample. It's going to go there. Then you notice there is light going through the sample as it's evaporated and ashed. Then we have two electrodes, and you have to cool it. And so this jacket here, you see the jacket, water in, water out, it's going to surround the graphite tube that is placed within two electrodes. And usually, if you remember when we were in the lab, I said, when we are dealing with graphite furnace, we use a 220 voltage, a higher voltage at the back of that's what we use normally to give us that high temperature. And those of you who have done AA, and those of you who are going to do it today, what we normally do is when you turn on the instrument, there will be the graphite furnace, graphite tube is not turned on, right? That is not turned on unless we're dealing with graphite furnace analysis. So notice again what we have said. All of the sample used is atomized in the furnace, in the electrothermal atomizer. The detection limit is about, notice there, 100 to 1,000 times lower than with aspiration methods. Aspiration methods would be encompass flame AA. And only a few microliters of solutions are used. So those are advantages here. Detection limit is low. Then many, for example, graphite, it's lower than flame AA. Sometimes it can beat ICP-MS, sometimes as you would see. And there's only a few microliters of solution that is used. And the basic principle, we know the basic principle of operation of electrothermal atomization or graphite furnace atomization. The sample is the sample container resistively heated to vaporize the metal atoms, and the sample is dried or the solvent is removed at about 110 degrees Celsius, and you ash the sample. What that means is burning off any other organic matter. And that's what that means, ashing the sample at about 200 to 300 degrees Celsius. Any organic matter, usually, that's ashing the sample. Usually, when you burn this off, ashing it, organic matter usually burns at that particular temperature, around 200 to 300. And the atomization, you notice here why these processes occur. Remove the solvent like water at 100 degrees Celsius. Water can boil. You can heat it up at a higher temperature. Boiling point is 100, but you can heat it up to about 150 to vaporize it. So you would normally vaporize it at about 110, ash the sample, that's you burn off any organic matter, and then you atomize it. Now that is the critical step in which now you are exciting the atoms from the ground state to the excited state, which occurs about 2000, 3000. And then from there, once you atomize it, you are exciting the atoms, putting them in the excited state. Then it interacts with the radiation. And then from there, it can absorb light, right? And then from there, you get your results and you compare your results with what you need to know. So then notice a disadvantage of this is poor reproducibility. It's poorly reproducible unless usually you take a lot of caution when you are dealing with graphite furnace. It's a tedious process. You have to sit there, adjust the part length normally. You have to adjust the part length, you have to adjust the height, and it's a tedious during the setup. And once you tear down, and then you have tomorrow, then you have to do the same thing. And so poor reproducibility detection limits are low. You can see here, ppb levels, 10 to minus 10, 10 to the minus 12 grams. Those are possible, right? So those are disadvantages. However, we have advantages for samples that need to be heated at higher temperatures, okay? All right, and these are questions I ask in an exam, either multiple choice or just what type of questions, okay? Now, this, for example, is an illustration cut off of what you see in a graphite tube. This is one type of graphite tube. You see the way it is shaped here, in here, where I'm pointing the arrow here. You see there is a hole here. There is these two electrodes. So notice this is, for example, one way. And you can see here another one here, the graphite tube. Here's another one here. So again, light is going to come from here to there. And you can see you have to use, for example, the holocathode lamp to produce the amount of radiation for that particular metal, right? So there are various types. These are very common, this B and C, you'll see that. And simply that is the graphite tube. And you put it within the two electrodes. Okay, the performance characteristics of electrothermal radiation. We have said electrothermal atomizers offer the advantage of unusually high sensitivity for very small volumes of the sample. Those are two advantages. Typically, we have said 0.5 to about 10 microliters usually, and therefore absolute detection limits lie in the range of 10 to minus 10 to the minus 13 grams ppb levels, typical ppb levels. Here are the advantages. One, usually high sensitivity, small volumes in the, these are small volumes that we usually use. And if you are limited by volume, remember, AA is very wasteful. Although it is reproducible results with high precision, it's very wasteful. The other thing we gain from AA, the graphite furnace over flame AA, is the fact that you don't have to go through the many tedious solution preparations. So that is an advantage of graphite AA. Apart from the setup that takes time, you don't go through the tedious solution preparations. You can use solids, you can use liquids in a graphite furnace atomization. All you have to do is to place your sample at the spot, which is going to be evaporated, and then it interacts with the radiation. Furnace methods are slow typically. They require several minutes per element because of the process. Remember the three processes. What are the three processes again? Process number one, prime. Number two, ashing, and then atomization. So the first step, actually, if you were to do it, I know how it works. You would see a graph. The first graph will be for evaporation, right? Then you will see the temperature rising from 100 to 2000, right? You can draw the graph. So normally you will see a graph that typically is going to look like this. You have a graph here, that stage and that stage and that stage. Those are the three stages. From about 0 to 100, 110, 120, depending on the setup. That's evaporating the water and then ashing it. And then from there, the atomization step. Okay, so the furnace methods are typically very slow because of the three stages. And a final disadvantage is that the analytical range is low. Usually, that's why it's not precise. It suffers from precision. But nevertheless, we use it because of the low detection limit. Okay, so we have talked about that with AA, with summary of the AA instrument for atomic absorption, consists of a radiation source, a sample holder, wavelength selector, detected, and a signal processor readout. You have a sample holder. We all know what the sample holder will be. What is the sample holder in AA? That's the flame. That's where you put your atoms. And like UV, where you put your sample in a cuvette. Or in IR, where you can either put it in a solid cup or mix it with a KBR pellet, right? So those are the things. The sample holder in atomic absorption instrument is the atomizer cell and contains the gaseous atomized sample. Perhaps I've gone through this first highlighted here in dark print here. Typically, this is what I expect now when you write your report. I need to see a radiation source. I need you to see the flame. I need you to show me if there's a wavelength selector or if it's a block diagram. If you are good in creativity, put that, and the detector and the signal processor. So that is what typically is involved in normally in atomic absorption. Radiation sources. What is the radiation source that we use in atomic absorption? The holocathode lamp. It's a holocathode lamp, and we can analyze. I showed you a table earlier. As many elements of the periodic table. Most of them are, many of them are metals. Okay, the radiation source is a graphite tube. No. The holocathode lamp. My mind is going ahead of it. Okay, is a holocathode lamp. So we have emphasized this. The holocathode lamp provides a narrow wavelength band width, and that's why it's used. So the bandwidth of the radiation source must be narrow relative to the width of an absorption peak. Remember earlier on the paper I presented to you from 1955. Remember the narrow range about 0. What? I don't remember those numbers. 0. I guess, what is
0.5 nanometers.
less than that?
0.1. No, 0.
It's a 2. Yes.
It was a lot lower than that.
0.2 zeros and a 2.
2 zeros and a 2.
Nanometers. 0. So it's so narrow and you need a bandwidth within that range. The problem was a problem created by limited width of the atomic absorption peak was solved by the use of line sources. And a holocathode lamp is a line source. It's a line source with bandwidth even narrower than the absorption peaks. Right? And then we say here, now, I just want to emphasize this, the diagram that we are seeing here. Now, notice here the disadvantage of using holocathode lamp. The advantage of AA is the fact that you need a separate lamp source for every element that you analyze. So all these other words here are trying to show you, let me show you the diagram, and then I will explain what those figure 10, 9, 10A, 9, 10B. So this is 9, 10A. You notice that there are peaks there, and you need a monochromator with a bandwidth in that region. You see that? If this is our lambda of interest, you need to filter these others out. So this is the emission spectrum of the source. And part B, you have to use a filter to remove these other peaks. And then from there in B, the sample absorption spectrum, we all know A equals log P naught over P. Is that correct? I want to pause there for a minute for those who have not absorbed that formula. Typically, A equals minus log what? T minus log T. That equation as written is correct. I want you to see A equals minus log T. And how do you measure transmittance? Transmittance is, so you calculate what goes out compared to the amount of incident radiation. P over P naught. You see that? So typically that's transmittance. So if you notice this is minus log T. So if you notice this is A equals log P naught. T is this, you flip it, then the negative doesn't have to be there. Does that make sense? So that formula is correct there. And I've just mentioned this because this common equation will come again. Now, you notice you have filtered that, and now this is the radiation source. You have to filter it. After you filter these other lines, or these other wavelengths, then you remain with this peak. Whenever after the radiation goes through the sample, you notice the emission spectrum after the passage through the sample and the monochromator, you see some amount of this radiation is absorbed. Hence, the height of the peak, as you see there, is increased. All right? So that is what the words were saying. We have to filter. We have to know the wavelength of radiation that we are going to use. And we make use of the holocathode lamp. Now, how does the holocathode lamp work? I need people to give me this information when they write their lab reports. How does the holocathode lamp work? It is the most common source for atomic absorption measurements. And this lamp consists of a tungsten anode and a cylindrical cathode. It's made up of a tungsten anode and a cylindrical cathode sealed in a glass tube that is filled with neon or argon at a pressure of 1 to 5 torr. Remember, we say that glass tube should be made of quartz. Remember, it should be made of quartz. And remember the pressure of neon. It's filled with neon at what pressure again? 1 to what? 5 torr. Now, why do we need neon within that tube? The cathode, as we all know, remember there is the anode and the cathode, a cylindrical cathode. And all those are sealed in a glass tube. That glass tube is filled with neon. It can be neon or argon, because they're most commonly used. Why do we need, you see, the cathode is constructed of the metal whose spectrum is desired. So if it is lead, then the cathode has to be metal black. Typically, that's what we have been doing. Those of you who have done the experiment, those of you who are going to do the experiment today. So the ionization, notice the process through which people thought about this from 1955. Remember, it hasn't changed much. Okay, thanks to Mr. Walsh. He solved a problem which we would use for many, many years. So what is the function of neon? Remember, there is neon within the sealed tube. The ionization of the inert gas occurs. Remember, we have an anode and a cathode, and you turn on the current. So then that current, when you turn the power on, you turn on the current, the anode and the cathode, and then you turn the potential. The inert gas occurs when the potential is on the order of about 300 volts when it's applied across the electrodes, and that generates a current of about 5 to 15 milliamps. Usually you will see on the lamp the current. You don't want to operate at that very high current for a newer lamp. You start at low current. If it degrades, then you increase it a little, right? And you will see what's going to happen. It's going to form, after it being sputtered, you'll see some black stuff on the glass because of the bombardment of those gases on the walls of the quartz tube. You will see that there are hollow cathode lamps. We can pull them out. I can show you that. Okay. Once it's used over and over, there is that bombardment that occurs on the glass surface. We call it sputtering. So if the potential is sufficiently large, 300 volts or more, the gaseous cation, remember the gaseous cation? First of all, you put some current. Argon then is converted to gaseous ions. The gaseous cation acquires enough energy. Remember what we are dealing with here. The hollow cathode lamp is made up of the element of interest, all right? So why do we need the argon within the tube? You need argon to provide you with argon cations, Ar plus cations. And those are going to bombard, you can see here, they're going to acquire enough kinetic energy to dislodge some of the metal atoms from the cathode surface. Remember, the cathode is made up of the matter of interest. And so once you have enough current, it dislodges the metal atoms, gaseous cations, convert the metal atoms, then they dislodge the metal atoms from the surface of the cathode. Where will those metal atoms go? Remember, it is cathode and anode, right? They would go to the anode. And so some of the metal atoms from the cathode surface, they produce an atomic cloud. That's what we call sputtering. And a portion of the sputtered metal atom are then in excited states. And therefore, they will then emit their characteristic radiation. Remember that these processes, think about this process this way. You have the gaseous cations. They dislodge the metal atoms from the cathode. The metal atoms will go to the anode, all right? And then they would fall back. They have to come back to the cathode. In that process, as they go back, they return back to the ground state, then they absorb the radiation. They absorb the radiation, characteristic radiation, because the whole cathode lamp is really made up of the metal of interest. A portion of the sputtered metal atom are in excited states and thus emit their characteristic radiation as they return to the ground state. Eventually, the metal atoms diffuse back to the cathode surface or to the glass walls of the tube and are redeposited. So that's simply they absorb a given amount of light, They get to the excited, and then they will return back to the ground state, giving off that amount of light. All right? The amount of light absorbed is proportional to the concentration of your sample. So maybe what the story that you're not getting here is this. Let me explain it. You have a hollow cathode lamp, right? It's on the other side. Remember how the AA is? The hollow cathode lamp is giving off light. So that light that when they return back to the ground state, that's the amount of light that is going to be projected onto your sample. And where's your sample? Where's your sample in the experiment? In the flame, not the fire, sir. It's the flame. Yes, it's the flame. So that's where your sample is, all right? So that's the radiation that the hollow cathode produces as the atoms come to the ground state, all right? And so that amount of light that's going to be absorbed by the sample is proportional. Now, however many atoms, however much your metal concentration, if the concentration of your metals is large, then it absorbs more. If it's less, then less amount of radiation is absorbed, all right? That's why when you plot it, it's absorbance versus what? Concentration. So the absorbance is directly proportional to concentration. And that's what I'm expecting in your introduction, how the hollow cathode works and how the whole process of determining the concentration works. Absorbance is proportional to the concentration. It follows Beer's law. Now, here is the hollow cathode lamp that we've been talking about. You notice here there is a glass shield here. There is this fork-shaped hollow cathode lamp here. All right, and then you can see here where you can see here, this is, you plug this to the, you plug this, okay, to the current, positive terminal, and then you have the anode. So you can see the anode here, you can see the cathode, and then you have neon here or argon at 1 to 5 tall, and then you have the quartz or Pyrex window. So here, this is the hollow cathode because it's hollow between the two forks. F-O-R-K. All right. Okay, so here is the hollow cathode lamp and what we call the electrode-less discharge lamp. Remember, we use the hollow cathode lamp. There can also be, that's one way. We have the electrode-less discharge lamp that we also use. The electrode-less discharge lamp basically works on the same principle of the hollow cathode lamp. The difference, you notice here, there's a quartz window here. There is an RF coil. What is RF? What? Radio frequency. And that's a radio frequency there. So it's going to generate the frequency there. Then there is a lamp in the middle here and a ceramic holder. Now the electrode-less discharge lamp, you see, does not have an electrode. So it's called electrode-less. Instead, you have a lamp which is powered by a frequency. Okay, it's going to be powered by some frequency. And these lamps produce only the spectral output from the elements of interest. They work on the same principle as the hollow cathode lamp. That's a development later after Mr. Walsh. And therefore are ideally suited to atomic absorption experiments. Yes, I'm going through the electrode-less. Is that what you're asking?
Well, if it's ideally suited for them, why aren't they like the widely used ones?
Let me go over this, and then I would answer that question. Why are they not used widely? You can think about why things are not used widely. Easy to handle, right? They might need more cost, fabrication. Those are the kind of things. Are they easy to generate radio frequencies that we need? Normally, That's those, because it's easy to produce a hollow cathode lamp. And most people find it easy in industry to do so. Okay, let me go through that. Okay. So the electrode-less discharge lamps, EDLs, they provide radiance intensities that are usually 1 to 2 orders of magnitude greater than hollow cathode lamp. A little bit more intense. But a typical lamp is constructed from a sealed quartz tube containing a few torr of an inert gas, such as argon, small quantity of the metal or the salt. Remember, for the electrode-less discharge lamp, you have a small quantity of the metal or the salt, and that is, you're interested in that. In the same way as the hollow cathode lamp, then you have these electrode-less discharge lamps of different ones, okay, to provide the characteristic radiation. Now, the lamp is energized by an intense frequency, radio frequency or microwave radiation. And again, on the same principle, just works on the same principle as the hollow cathode lamp. The ionization of the argon occurs to give ions that are accelerated by a high frequency component of the field until they gain sufficient energy. Now, electrode-less discharge lamps are available for how many? By this time, about 15 or more elements, not as many elements because of the fabrication, putting the salt all the time, okay? So that's why they are limited, and they will cost more. So that is the electrode-less discharge lamp. Now I want to get here before I stop on, remember, radiation source and the instrument on the single beam instrument, a typical single beam instrument. Usually, you know how a typical beam spectrophotometer works. Remember, it does not have a reference. It does not have a reference. You put the same spot. You can do first your blank, remove your blank, and then put your sample there again. That's the difference between a double beam and a single beam spectrophotometer. So usually it contains of several simple grading spectrophotometers with a photomultiplier transducer. So normally, even for a double beam, you're going to have a PMT. So will a single beam spectrophotometer. The only difference is in its construction. So usually the 100% T adjustment, remember what we say, 100 T adjustment with a blank. You have used spec 20. I'm hoping everyone has used spec 20 in your life here at the university. Anybody? You did this at the lower classes or wherever, spec 20.
What room is it in?
It's downstairs. We do this for freshmen, yes. Okay.
I did because of COVID.
Oh, you did online.
Mhm.
Okay. Oh, I see now. Most of you came through online. All right, let's do this. Let's say this. Normally, what happens if you have like spec 20, you look at it, it has only one slot. Okay. You put the blank water and say this is 100% T. All right. You just adjust it, calibrate it. You say all the light has gone through. And then that's your calibration. And then you put, remember, what is your blank? And then you remove it. And then you have a similar cuvette. And then with your sample and put it there. And then it reads, okay? So it's comparing the amount of light that is transmitted to how much has been absorbed. So this is what this sentence is saying here. The 100% T adjustment is then made while a blank is aspirated into the flame. Finally, the transmittance is obtained with the sample replacing the blank. Does that make sense? So usually in the same spot. So unlike double beam instruments, in double beam instruments, the beam from the hollow cathode lamp source is split to a mirrored chopper, one half passing through the flame and the other half around it. And the two beams are then recombined. You then can compare the two beams. One that goes 50% of the time through to the detector. The other one where a portion of 50% of the light goes through the sample. Then there is a comparison that's made. Typically, this is what you did in the UV-Vis spectrophotometer. And so the two beams are then recombined by a half silver mirror and passed into a grating monochromator. And the ratio between the reference and the sample signal is then amplified and fed into the spectrophotometer. Here is a diagram. So the first diagram here is what we saw earlier, okay, in the last, when I went through this. You have a lamp, you have a chopper here, then here is the reference power, PR. Here is the power that goes through the flame here. And so we are saying here is a half silver mirror. You have a chopper here dividing the light into the two. The split here, this is the reference, then you go back here, then go to the Sanitana monochromatic grating, and eventually to the PMT, which amplifies your signal. So this, notice there's light that goes through your sample, which is in the flame, and there is also light that goes through, that just goes through the reference. And then the two can be compared. Notice, initially, when you do your analysis, normally, like when you did the UV, you put two cuvettes, all right, on the reference and the blank, remember? Use acetonitrile. So that was then taken digitally, taken into memory. We're together there. And then you put your samples here, and then it keeps referencing the original blank sample. So, and then this is a double beam, as you see. What is lacking in this instrument here? Notice there is only a lamp and a flame. There is no reference. The grating is already there, just like you see here. And you have a PMT in the readout and normal. Okay. So you have a double beam and a single beam spectrophotometer. Now, we know the advantages of a double beam spectrophotometer. Once I cover UV, and then I would emphasize this again. I want to stop here, right? So then I've not finished what I wanted to do. I have about 10 more minutes to finish this section. And on Monday, what I want to start with is inductively coupled plasma. Okay, so I will finish this on Monday. Typically, now I want to tell you this. Can I flash forward here a little bit for us to help some of you, those of you who have